In electrical circuits, analyzing the flow of current and the distribution of voltages is essential for understanding and designing circuits effectively. Kirchhoff's laws, formulated by Gustav Kirchhoff in 1845, provide a systematic method for solving complex electrical circuits. These laws are based on fundamental principles of physics. Law of conservation of charge for Kirchhoff's current law. Law of conservation of energy for Kirchhoff's voltage law. Why are Kirchhoff's laws important? They enable the analysis of circuits with multiple loops and nodes that cannot be solved using simpler tools like Ohm's law alone. They help in determining unknown quantities such as current, voltage, or resistance in circuits with interconnected components. They form the basis for advanced circuit solving techniques like mesh analysis and nodal analysis. Practical applications. Electrical engineering. To design and analyze circuits in devices like smartphones, computers, and household appliances. Power systems. For distributing electricity efficiently in grids and networks. Electronics. In developing circuits for signal processing, communication, and control systems. Let's start Kirchhoff's laws. Kirchhoff's first law, also known as Junction law or Kirchhoff's current law, KCL. It states that the total current entering a junction is equal to the total current leaving the junction, or the algebraic sum of the currents meeting at a junction is zero. Let's try to understand the meaning of this statement. The concept of algebraic sum refers to the addition of quantities while taking into account their associated signs, positive or negative. In the context of Kirchhoff's current law, this means summing up the electrical currents at a node or a junction with their respective signs. Currents flowing into the junction are assigned a positive sign. Currents flowing out of the junction are assigned a negative sign. This convention is opposite in nodal analysis. But for now, just remember this convention that the entering current will have the positive sign and the leaving current will have the negative sign. Let's consider an example where 5 currents are meeting at a node or junction. Currents at the junction. I1 is the entering current. I2 is the leaving current. I3 is the entering current. I4 is the entering current. I5 is the leaving current. Thus, at this junction, entering currents are I1, I3, and I4. Leaving currents are I2 and I5. To calculate the algebraic sum of currents, we consider their signs. Entering currents have a positive sign. Leaving currents have a negative sign using the sign convention. I1 plus I3 plus I4 minus I2 minus I5 is equal to 0. This equation can also be written as I1 plus I3 plus I4 is equal to I2 plus I5. This shows that the sum of entering currents equals to the sum of leaving currents. Live example. Imagine a water pipeline where water enters a central tank through 2 inlets, 3 liters per second and 2 liters per second. The total water leaving through the outlet must be 5 liters per second to conserve water flow. Physical meaning of sign. The signs reflect the balance between incoming and outgoing charge, ensuring no charge accumulates at the node. Kirchhoff's second law. This is based on the principle of conservation of energy. This law implies that the total energy supplied to a closed circuit is equal to the total energy consumed within the circuit. Energy conservation ensures that no energy is lost or gained unexpectedly as the current traverses the loop. Suppose you go for a walk and at some point you meet a number of friends. Now at n, total number of friends you met is equal to number of friends at path. The same applies to the current. When it travels along the circuit, its magnitude keeps in changing according to the product of current and resistance or EMF connected in the circuit. So it states that in any closed circuit, algebraic sum of product of current and resistance and the sum of EMF connected in it is equal to 0. Or in any closed circuit, algebraic sum of potential difference is equal to 0. The algebraic sum considers the sign conventions. Positive for energy gains moving from the negative to the positive terminal of a battery. Negative for energy losses, voltage drops across circuit elements. In simple, remember that in a circuit, if the loop direction and the current direction are the same, the sign convention is taken as negative. If they are opposite, it is taken as positive. For a source, when moving from low potential to high potential, the sign convention is taken as positive. When moving in the opposite direction, it is taken as negative. Before we start to explain Kirchhoff's second law, let us recall Ohm's law. Look at the diagram to understand how to find the potential difference across the resistance R. The potential difference V is given by V is equal to IR. Apply Kirchhoff's second law to the circuit shown in figure. For a loop ABCDA, the loop starts from A to B. Here the loop direction is from high potential to low potential, so the sign convention is negative. Again, from B to C, loop direction and current direction are same, so the sign convention is negative. From C to D, also loop direction and current direction are same, so the sign convention is negative. From D to A, loop direction is from low potential to high potential, so the sign convention is positive. So we can write minus E2 minus IR1 minus IR2 plus E1 is equal to 0. If you want to practice it, see the figure and practice it. This is for practice purposes only. You can write either this or the previous one in the examination. Thanks for watching Pathfinder 6. Like, comment, share and subscribe to my channel.